Hello everyone, welcome back. In this video I'm going to explain an example of distribution of load in slab in a complicated case. Not just one slab, we have different combination of slab, one-way, two-way slab together with load calculation. Now if you read the question, it says that for the plan given below, live load for the corridor is 3 kN per meter square. So the corridor has a live load 3 kN per meter square, and for the offices are 2.4 kN per meter square. So the offices, they have different live load than the corridor. Then it says the slab is 150 millimeter thick. So we know there is a slab, basically those corresponding for the beams A, B, B, C, D. The blue lines corresponding the beams, and it says sketch the loading that acts along member GHC. So it's recommended or it's requested to draw these beams distribution, the load over this beam, live load and dead load together, so we have to add them together. We're not gonna go for factoring the loads here, we're just trying to do them separately or add them together in order to get the result. Unit weight of reinforced concrete is 24 kN per meter cube. Now here we need this unit weight in order to calculate the dead load of the slab, since we know that in order to calculate dead load, we need the thickness of the slab multiplied by the unit weight of concrete. Now the thickness here, it's in millimeter, so 150 millimeter. This is kilonewton per meter cube, so we have to change the units in order to be consistent. So we can say 150 over 1000, so I'm changing it to meter, and multiply by the unit weight that we have it there. Now let's point. The result of this will be kilonewton per meter square. As you know, on the slab, load will be given as kilonewton per meter square. Now if we would calculate this value, we have 3.6 kilonewton per meter square. This is the dead load. And now since we have different rooms, and each of them their live load different, so we cannot just say 3 plus 2.4 plus 3.6. Now on the corridor we will have the summation of dead load plus live load for the corridor will be different. So the dead load everywhere is the same. Why? Because the slab, we only have one thickness, 150 millimeter for all the slabs. So the dead load from the slab comes 3.6. So W, which will be the weight in the corridor, on the corridor, 3.6, which is the dead load of the slab, plus the live load in the corridor, which is 3. So here we have 6.6 kilonewton per meter square. On the other hand, for the offices, in both offices, W would be 3.6, which is the dead load from the slab, plus the live load of the office is 2.4. It's gonna be 6 kilonewton per meter square. Remember here we have different, and that's happening in real life when you're calculating dead load and live load. So you remember from the tables that we're collecting live load, depending on the occupation of the building and the usage of the room, live load is changing. That's why I brought this example to be somehow close to the practical calculation, and you will see that how we're dealing with different type of slabs in this manner. Now we have the W, which is the weight on the slabs. Now here it's clear how many slabs we have it. So we have a corridor, which is one slab here, and I have two offices, so we can say we have 3 slabs, 1, 2, and 3. Now one by one we will go through them to see whether first if they're one-way slab or two-way slab. Then if we know they're one-way or two-way, we will draw the distribution as we know. Then we'll calculate the way that they will distribute the load. First slab, if I take into consideration, now this dimension is 2 meters, the other dimension of the corridor will be 9 meters. If you remember, we said that long side over the short side. So if the long side I have it here, it's 9 over 2, it's 4.5. Sorry. So we have 4.5, which is greater than 2. I mean, if you write greater than 2, it's no need for this equal here. Greater than 2, so we have one-way slab here. One-way slab. That's the first one. For the second, which we have this office, it's 4 by 5. So we'll say 5 over 4, the long side 5 over 4, which is going to be 1.25. Now this is smaller than 2. This is two-way. And then the other one we have it here. Four by 4 we have it. So for the third slab, 4 over 4, it's going to be 1. It's smaller than 2. Again, we have two-way slab. Two-way slab. Now we have two-way slabs, one-way slab. Now how does this gonna help us to do the things that we have it? Now we know the distribution in the one-way slab or two-way slab. So if I'm going to provide the distribution that we have it here, we know that the distribution, it's going to be for the one-way slab, we set it in the kind of middle. Let's do it manually. So we know that the load will be distributed to the long side. That's what we said in the. So we said that half of this load in the corridor, half of it will go for this long side, the other half for the other long side. That's what we know for one-way slab. For the two-way slab, what we said, there's two types of two-way slabs, rectangle or square. The square one, which we have it here, 4 by 4, and we have one rectangle, 4 by 4, 4 by 5. We have both of them. For the square one, we said that since you go with 45 degree, and if you go with 45 degree from this corner, you will reach to the other corner. The same thing from this corner, you will go with 45 degree, you will reach to the other corner. So this triangle load will go to here, and so on. The other triangles will go for the corresponding beams. And this is this one. For this, which is 4 by 5, we said from the short side you will start, and from the short side you will draw the 45 degrees. They will meet somewhere. They will not go from corner to corner because it's rectangle. And from the other short side you will draw something like this. Remember please, you start with the short side, then you will connect them along the long side. So remember, in the rectangle you will start with the short side, you will do this small. By the way, how would you know this one without memorizing it? I mean, this is 45 degrees, yes, 45. If it's 45, you know that this will be 2, and this side also will be 2. Because if it's 45 and it's 4, half of it will be 2, the other half is 2, and this side will be 2 as well. The same thing for here. Now it makes sense, yes, because 2, 2, 4, and this distance here is 1 meter. It's not to sketch, but at least it will be something more. I mean, this 1 meter will be a bit smaller if you draw it to the sketch and to scale. So this is 2, 1 meter, 2 meter, total will be 5 meter. For here, if you look at it, since both sides 4 meter, 4 meter, you know that this is half, 2 meter, 2 meter will be. For the one way, directly the middle of these two, so this is 1 by 1. 1 meter, 1 meter. Now the distribution we have it here, look, this triangle will go here, this trapezoidal will come down, this triangle goes to this beam here, and this trapezoidal will goes to the beam here. Now in the question, it was asking us to draw the sketch of the beam GHC, a distribution of the load on GHC. Now how many loads are transferring from the slabs to the GHC? From two sides. Now remember, if the beam is interior, from both sides the slabs will send load to it. Now here we have from this corridor, the load will go to GHC, which you see it with this distributed. We have a rectangle goes to there, and on the other side we have from two offices. One office will send this triangle, the other office will send this trapezoidal. So if I just take the part that I want, like we know this one now, but I don't want everything. I'm just gonna highlight the part that I want. Now again, I'm gonna go over them. I only need since I'm not gonna draw every beam's distribution, I'm only aiming this beam, so I only leave the part that I need. This is coming from that side, and here, because I have to explain something that I've seen from many students. Remember, we are still on the top, still working on the top view of the plan, we call it. Why? Because I've seen a lot of students, they feel that this is upward and downward loads. Do not make that mistake if you're listening to me. So those loads, all of them are downward, but we're looking at the top view. What we said that try to make this one in a 3D manner. So if I try to make this one in a 3D manner, I'm not going to draw everything. Let's try to draw. This is the corridor, we have it. And if I continue like this, this is the kind of the room. What we said that the load that you have them, try to convert them into vertical, downward load, or to rotate those 90 degrees. So kind of, it's somewhere here, yes, I just draw it for you to see what do I mean. The load that you see on the plan is like this. I need you to see it as a 3D. It's like this, but what will we do? We will just rotate this one 90 degrees. We'll try to bring it over the beam. Since we want, this load is acting in this manner, it will be 90 degrees acting like this. The same thing for the other two load. We have this triangle load here, what will happen if I rotate this one 90 degree? I'll bring it over the red one as well. So I'm going to put it over. Look, what will happen? I will add it to this place here, like this. I'll just try to bring it over the beam. This is, well, I brought it over this one. The same thing we have what we have here. We have a trapezoidal load. We have it here, look like this, and I'm taking this trapezoidal over the red one because all the loads will be on the beam. So I have a trapezoidal load here as well, goes like this and goes down. Remember, I'm doing this one in 3D. You don't need to do it in 3D, but it's easy to understand what we're doing. This is plan view. This is the plan view, we have it. This is the 3D. So in the 3D, we said those on the plan. I want you to know that those are not upward and downward. I've seen a lot of students say, okay, this is downward, this is upward. They will cancel each other. There's no such things. We're doing on the plan view, all of those loads are going to the beam. So you will do it in this manner, in such manner. Well, in order to make it easier, we're not, as we say, we're not drawing 2D, 3D. What we will do, I'm gonna draw this one in the elevation. Look, when we go to elevation, what we will do, in the elevation, we will draw a beam. Now this is the beam, I have it. Well, the point of the beam that we have it there, so we have what? If you recall, this point here is G. So this is G, this is H here. This is H, and this is C. I'm going to draw GHC in the elevation. So I'm going to look at it in this manner. We'll draw it in this manner. We're looking at the GHC from the side, which we call elevation, will be something like this. Now for the support here, since there is, I haven't provided any columns there, you can just provide any type of support that you prefer here. Don't mind any support that you're providing it there. Since we're not doing analysis of this beam yet, that support can be columns, can be anything. Just keep it in this manner, it doesn't matter. Now, what do I need? I need a distribution. I know that there is one, sorry for the line I'm trying to draw it. So we have one. This was coming from the corridor. Then we have trapezoidal. So the trapezoidal, we have it there. The dimension kind of, we can manage them. Here just drawing the shape. So we have one trapezoidal. Still I haven't calculated their value. I'm just trying to draw the distribution. And from the other side, we had one triangle. Now look at here, this is how we have to present the loading on the beam, not in the 3D, not in the plan view. The plan view will help us to get the areas. So rectangle, one rectangle, look, this rectangle for the corridor, it's at the bottom. Then this from the office, the trapezoidal, I will put it here, so you see that coming from there. Since we know this is 5 meters, we have it here. We know this is 5 meters. And we know this distance here, 4 meters. And for trapezoidal, if I want to make it more detailed, we know for the trapezoidal as well, this part for the trapezoidal, it's 2 meters. This part is 1 meter, then we have 2 meters for the trapezoidal. If you ask me where do I get this 2 meter, 2 meter, 1 meter for trapezoidal, I'll tell you that we'll get this one from the here. When we did the distribution, we said with 45 degree will go, since the 45 degree will go for the short side, so it will be 2 by 2, so you see it here, 2 by 2, then 1 meter, 2 from the other side, 2 to 4, since the total is 5, 1 meter will remain for the middle. If you make it much, this part will be smaller than the 2 for sure, but it doesn't matter here. Now so far I just got the distribution, and I can say that this is G, this point here is G, this is H, and this is C. Still I haven't finished. Why? Because I have to find three values. I can call this one W1, which is for the rectangle at the bottom. I can call this one W2, which is for the trapezoidal, and W3 for this triangle. Three W's, I have to find them. Where do we get them? If you remember, we said that on the beam, there is one equation that we follow. It always will be similar. The W on the beam. So W on beam, if we do W, which is on the slab, which is kilonewton per meter square, and the result of this one will be what? On the beam will be kilonewton per meter. Remember, we'll get kilonewton per meter on the beam. We said that W on the slab, or W of the slab you can say, multiplied by what? By the short side of the slab divided by 2. By the short side divided by 2. Now for each slab, short side will be different, remember. You have to be careful. For each slab, short side, it might be different. Well, we'll start with W1. W1 is for the rectangle, which comes from the corridor. Then I'm checking the corridor. The corridor's short dimension is 2 meters. Then, if I want to calculate W1, we'll say that W of the corridor, which we already know W of corridor as well, we have it here. W of corridor is 6.6. So W of the corridor 6.6. Short dimension of the corridor is 2. So if I want to calculate W1, which is here, that comes from the corridor, I'm using this equation here. So I can say that W1 is equal to, since coming from the corridor, 6.6, this is W on the slab of corridor, kilonewton per meter square, multiplied by the short side of the corridor, it's 2, divided by 2, so it kind of became 6.6 kilonewton per meter. Like this is 6.6 kilonewton per meter is W1. I'm going to go for W2. W2, I gave it to this trapezoidal, so I'm going to go for the trapezoidal coming from this office, which first I need a W. For both office, the W is 6. Okay, that's good. Then I need for this, the second slab office, we have it here. The short dimension is 4. For this one also the short dimension is 4, isn't it? Because 4 by 4 for this one also the same. So for both of them, since the load is the same, the short dimension is the same, so W2, W3 will be the same in that case. W2, W3 will be the same. Why? Because the load is the same, the short dimension the same, so I can just rewrite both of them under each other. For W2, the load on the slab is 6, multiplied by the short distance is 4 divided by 2. That's going to be 12 kilonewton per meter. For W3, similar, the load on the slab is 6, short dimension 4 divided by 2. That's going to be 12 kilonewton per meter. Now I got those results, but I have to do what? I have to bring back here and write them. So for W1 is 6.6, the other one 12. So W1 here, 6.6 kilonewton per meter. However, I will write it like this here, but it will not be true. If I write this on 12, it will not be true. Kilonewton per meter. This will not be true. Why? Because in structural analysis, when we're providing W, we will provide the height from the top to the bottom. So what does that mean? We have to provide this one from here till the top of the, from the top of this one to the top of let's say the bottom of the load, or the top of the slab. We need to present this one not like 12. This 12 does not mean from here till here. So in order to make this one the way that we have to presenting it, yes, this 6.6 is okay. Why? Because it is from here to the beam. That's correct. But for the one over here will not be correct. What will you do? You will add this 6.6 to the values. Here we have it. So in order to present this value here, I cannot say present as 12. I'll present as 12 plus 6.6, which will be 18.6 kilonewton per meter. Same thing goes for here as well. So this is only this part. But since we have to present it from the top to the bottom, so it will be again 18.6 kilonewton per meter. Now I'm just gonna just redraw this one nicely and present the final drawing of the slab. We have it there. So if this is the slab, I have it, sorry, the beam, I have it here. We said that doesn't matter how do you present this, the slabs or the supports. Now what I'm going to do, I'm going to draw it in a way that, so there is the load, we have it here, it goes in this manner, and then 1 meter goes, then it comes back somewhere here, then same level, then goes up, and then comes down, same level that we have it there. Now to present the load, you have to present it as this way. I mean, this is, you can still make them as a rectangle, trapezoidal, whatever you want, but this is how does it look like. So at this point here, at this point we have 6.6 kilonewton per meter, which is the same point at this one here, 6.6 kilonewton per meter, which is going to be the same point here, 6.6 kilonewton per meter. The top value we have it here, it's 18.6 kilonewton per meter, goes for the same here, 18.6 kilonewton per meter. And for the dimensions that we have it here, we say that this part here and this one is 1 meter, this is 2 meter, so we have 2 meter, 1 meter, 2 meter, and for this one it's in the middle as well, total was 4 meter, so 2 meter, 2 meter, G, H, C. And that will give you the distribution of the load on the requested beam that we have. Now if you go back to the beginning, you would be able to do for the rest of the other beams. Why? Because everything starts from here. Now you can take any beam and you can draw the distribution. AG, there is no load going to AG because there is no arrows pointing to AG, and the same thing, BC will not take any load directly from the slab. Where does the EH, you can do EH, and by the way, there's something else I haven't finished it yet, sorry, still one remain, because for GHC, look at this point here, point H. When the load, this two load going over EH, what will happen later? Half of the load will go to point H, half of the other load will go to point E. I'm not going to do this one here. Why? Because if I assume that there is support at H, will not do this calculation. If there is a column under H, no need to do this calculation because the column will take all the things there. But if there's, let's say I'm taking this one here to explain this to you. Let's say if I don't have column, if I don't have column at, let's say if I provide some columns, let's say there is at A, there is a column, I have it, if I have a column at B, now the location when there is no column, we shall provide a point load. If there is a place, a connection between beams, and there is no column, remember this please, you have to provide a point load. Let's say I have it like this. There's only one point that there is no column, which is H, and the interconnection of these beams, we have to provide a point load. So where do we provide the point load? Normally, we provide the point load on the long beam. On the long beam. Why? Because the short one, it's giving the load to the long one. So when the load from this office goes here and from this office goes here, they will send it to H and E. We're not going to do anything on E if there is a column, but H, if there is no column, we have to provide the point load on H. I didn't provide the columns here, so basically I can leave this calculation. But if you want to do it, what will you do? You have to draw the EH distribution, the beam EH, then find the reaction and bring the reaction on H. This is what you have to do. For the example that we did here, if we want to provide a point load here, a point load at H here, this will be what? The reaction of beam EH after taking the two distributed load, those two triangle. I can show it to you here. This will be something like this. So you have the two from the two side. So you have from the two side this will come over it. Then there will be one big triangle over here. By the way, adding triangle to triangle will still end up triangle. Adding triangle to triangle will be still triangle, but the value will be. Then you will find the reaction, and there will be a point load at this point here. The reaction of this beam here. Of this beam here will be there. If there is no column. But if there is column, then no need to do this calculation. I believe this is enough in the one-way slab, two-way slab distribution. And this had also calculation of dead load. When it's a dead load of the slab as well, calculated from the scratch. If you want to practice, you can take the others. For more practicing what to do, try to remove this column here. For example, removing this column even here. So if there is no column at this, let's see, even at G, I'll remove the column. So what we have to do here, it's only putting 4 columns there. In order to understand that the beams will transfer the load after to who? To the column. So a fast way of explaining, if this gives to this one, let's say we know that this is going to give it here, those way. Then from the beam, you have to find the way of the load to the column. Look, any arrow that you're pointing it to the beams, they have to find their way toward the column. I'm starting with these two. Let's say these two here. This one and this one. Where they will go after? Sure, they will go like this, yes? They have to go to the other end. This way and this way down. Then what will happen from there? From this point? For sure, afterward it goes to C. And from C will go where? It can go here and some part will go to D. The same thing for this one. It comes to E, some part will go to F, some part will go to D. Look, each load will find their way to the columns. From the slab, we'll give it to the beam. From the beam, it goes to the column. So it means that if you're trying to understand how the load is act, you can just change the location of the columns and it changes everything. Because the distribution of the load, yes, when it goes to the beams, it's still the same. All the beams, they will take the load from where? From the slab. The distribution will still be the same. But later, where will be the point load? For example, for sure now we have a point load at G. If I want to draw AGF, look, if there's column, yes, there's the column at A, there is the beam I have it, and there's the column at F. Look, I'm drawing it like this in order to make sense. This is A, this is F. Where's G? G is somewhere here. So if G, there is no column, and there's this beam it's connected to G, yes? So what will happen? The load from here will come to G, and there will be a point load here. We will have a point load at the connection when the beams are touching each other. Remember, any intersection for the beams, there will be point load if there is no column. Like we're expecting to have a point load at H. You're expecting a point load at E. You're expecting a point load at C. Why? Because they don't have, look, 4 points. I selected, yes, 4 points. Why? Because there is no column and the beams are touching each other. I'm expecting to have a point load. Remember this, please. This will help you to understand better. When there is no column, it will provide the intersection of the beams as a point load over each other. That will be enough for this example. Thanks for listening.